Recall that whenever an electric current is moving through a very long straight conducting wire, it produces a magnetic field. Now the direction of our magnetic field can be determined using right-hand rule number 1. Now what about the magnitude? In this lecture we're going to see what the magnitude of such a magnetic field is that is produced by an electric current moving through a very long straight conducting wire. So once again, let's begin by recalling that an electric current moving inside a very long straight wire produces a magnetic field that forms concentric circles around that particular straight wire. So let's suppose we have a very long straight wire that runs along the y-axis as shown in the following diagram. Now our electric current moves in the positive direction along the y-axis. To obtain the direction of the magnetic field as a result of the electric current in such a straight long wire, we apply right-hand rule number 1. So we take our right hand, we extend our thumb, and we wrap our fingers around our wire so that our thumb points in the same direction as our electric current. So we wrap it in the following general direction. Now the direction of the magnetic field will be in the same direction as our curling fingers. So that means our magnetic field will form concentric circles that will point in a counterclockwise direction. Now that's the direction of the magnetic field. And recall that magnetic field has both direction and magnitude. It's a vector. So the magnitude of our magnetic field B, which is given in Teslas as a result of a very long conducting wire, is given by the following equation. So we take our proportionality constant mu naught divided by 2 pi and multiplied by I divided by R. So our mu naught is simply a constant. It's known as the permeability constant of free space, and it has a value of 4 pi multiplied by 10 to negative 7 Teslas multiplied by meters divided by amps. Now the I is simply our electric current flowing through our conducting wire given in amps, and our R is simply the perpendicular distance from our conducting wire given in meters. So we see that as our electric current is higher through our conducting wire, it produces a stronger magnetic field. And if we examine our magnetic field at points further away from our conducting wire as R increases, that implies that our magnetic field decreases. So the higher the I, the stronger our magnetic field is. The higher the R, the lower our magnetic field is, the weaker our magnetic field is. So let's look at the following two examples. In example 1, suppose that a very long straight wire carries an electric current of 50 amps in a positive direction along the y-axis as shown in the following diagram. So determine the direction and magnitude of the magnetic field produced 25 centimeters away from our conducting wire. So once again we have the following diagram, which is essentially the same diagram as this diagram. So to find our direction, we once again apply right-hand rule number 1, and we see that the direction of our magnetic field forms a concentric circle that points in the counterclockwise direction around our electric wire. Now, we want to calculate the magnitude of our magnetic field at this point, 0.25 meters away from the center of our conducting wire as shown. So we simply take the following equation and we multiply out our values. So mu naught, which has a value of this quantity divided by 2 pi multiplied by 50 amps divided by 0.25 meters. This quantity is 200. We multiply 200 by this ratio and we get 4 times 10 to the negative 5 Teslas is our magnetic field at this position. Now Now, let's look at example number 2. Let's suppose we have 4 wires that carry an equal electric current. Determine the magnetic field in the middle, assuming it's an equal distance from each wire. So we have the following 4 wires: wire 1, wire 2, wire 3, and wire 4. Now, the electric current in wire 1 and 2 point out of the page, while our electric current in wire 2 and 3 are going into our board as shown by the following X's. So we essentially apply right-hand rule number 1 to determine the direction of our magnetic field exactly in the middle of these 4 wires. So let's begin with our electric current number 1. So it is coming out of the page, so that means we wrap our right hand in the following manner so that our thumb points out of the board as shown. So that means the magnetic field at this point, as a result of our electric current 1, will point in the following direction. Now we continue the same exact rule for 2, 3, and 4, and we get the following diagram. Notice that because B1, the electric field as a result of electric current 1, and B4 have the same magnitude because they have the same current. And because our distance is also the same by this equation, B1 is equal to B4, but they have opposite signs. So that means these will cancel, and the same exact thing can be said about these 2 magnetic fields. B2 is equal to B3 in magnitude, but they have opposite signs, so that means these will exactly cancel. That implies that the magnetic field will be 0 because all these 4 magnetic fields will cancel one another out.